Welcome to Lesson 12, an Intro to Experiments. So we're going to talk about how they're designed, at least at a basic level, and we're going to also talk about blinding and bias. Okay, so a statistical experiment, one, it imposes a treatment or more than one treatment, and the entire goal of an experiment is to isolate the effect of these treatments. So you might have the two or more groups and you have collected whatever variable. You can argue that the main difference between these two groups, what caused the difference that you observed, was the treatment. So the whole idea is to isolate, this is the effect of this treatment. So use it when you compare control groups in a randomized experiment. It's also used to determine a cause and effect relationship. So remember, you can't determine cause and effect relationship with an observational study, but with a randomized experiment, you can. Okay, so the Minnesota study of twins reared apart is a study where they have 56 pairs of twins, identical twins, and they are reared apart, so they are raised separately, and they come back after a while, probably when they're adults, and they go ahead and record information on all of the twins because they want to compare the twins. So is this study an experiment or an observational study? Okay, so one thing to consider is what makes the two groups different from one another, right? So you have twin 1 and twin 2, sort of, How do you determine which environment each twin is raised in? Well, a researcher does not usually determine that. That's super unethical, right? You don't get to. They're reared in whatever environments their parental units determine. So this would be an observational study. We observed pairs of twins that got split up. We did not, as researchers, I say we, it's unethical to split them up and then randomly assign where they live. That would be really unethical. So here's another one. We have a big study, 5,200 patients that were categorized into two groups. So they asked these 5,200 people, how much do you drink soda? And they split them into two groups. So there was a regularly drink group and a sparingly drink, so rarely drink group. After 4 years, they follow up and they determine whether or not the individuals in each group got heart disease or not. So does soda use cause heart disease? So things to consider. There are two groups, right? Regularly drink and sparingly drink. How did people get into those two groups? If we randomly assign them into those two groups, we have an experiment. But I don't know about you. I would hate to be the researcher trying to randomly assign people to regularly drink soda or rarely drink it for 4 years. People won't listen to you. They won't. They'll do what they want. So this is not an experiment. I would argue this is not. So then you need to consider is, both of these say it's an observational study, but can we use that causal language? Can we say drinking more soda causes heart disease? So thinking back, you can only say the cause like if it had been a randomized experiment. This is something that would actually be very, very difficult to use as an experiment. And sometimes there are ethics involved, right? Suppose I wanted smoking, does it cause cancer, right? I can't randomly assign some folks to never smoke and some folks to heavily smoke. That would be super unethical. So I really have to rely on observational studies because of ethics. So note that sometimes it's difficult because you want to have an experiment, but it's not ethical. Especially if you know that one or more of the treatments cause harm. It's not allowed. So the principles of an experimental design. So the first thing is replication. And I really want to focus on this one because a lot of folks misunderstand this one. So it's having more than one experimental unit in each treatment group. So this means that you apply each treatment to more than one individual. So if I have a new cancer treatment and an old cancer treatment, I have to apply each treatment to more than one individual. That's what this means. This does not mean repeating the experiment. This means that we have more than one experimental unit in each treatment group. That's all that means. So absolutely this makes our results more valid, because if you turned out to say, hey, look, I cured cancer in this group, but your treatment group only has one person, who's to say that wasn't a fluke, right? We don't know that that's something that would consistently happen. There was only one individual in your treatment group. So it really does add validity to have more than one individual. Ideally, we like to have more than two as well. Second there is randomization. So this is necessary for cause and effect. So if you want to say, hey, variable A caused this change in variable B, you need randomization. It helps reduce the bias due to unknown sources. It basically makes the two treatment groups as similar as possible so that the main difference between the two groups is the treatment. So we can isolate just the effect of the treatment. And then control. So this is a really, really important one. I've been a statistical consultant in cases where there weren't a control group. That was really problematic. So this helps us compare to a baseline. It's super, super important. Minimize external sources of variation. Basically, it gives you a baseline to compare to. You don't want it to compare to nothing at all. If I had a new cancer treatment and I had a new treatment group with just that treatment, well, I don't know how it compares to the standard treatment that's already out there. And that is a problem. And then just to, we'll get back to this phrase. When an experiment concludes there are differences, there's a phrase that we use, statistically significant. And when people say things are statistically significant, it means that the difference that we observed was large enough that it's not likely it would happen by chance. So we'll really get into that later, but just an intro. So randomized experiments. So the most basic one that we have is a completely randomized design. So here I have all my experimental units, and then I have two treatment groups, so treatment 1 and treatment 2. So I take these 10 experimental units, randomly select half of them to be in group 1, half to be in group 2, and then those are my treatment groups. So these 5 that ended up in group 1, that's my treatment 1 group. These 5 that are in group 2, that's my treatment 2 group. So then I'll go ahead, I'll apply the treatment and record whatever the response variable is. Then you compare. So summarize and compare is just compare the results in the two groups. And the idea here is the probability of me selecting these 5 to be in group 1 are just as likely as me picking any combination of 5 from experimental units 1 through 10. So here we have a design, it's about tomatoes. We have 10 tomato plants, and they're going to receive a chemical solution or nothing. So, and we want to look at tomato yield. I'm not sure what you measure it in. It could be in weight, it could be numerous things, number of tomatoes, I don't know. But yeah. So to start with, response, it's what I'm measuring. That's my tomato yield. Factor, so I have two groups. What makes them different is what they receive. So their chemicals given. So the levels, and you could probably reword this slightly differently. It's going to be the solution that they're interested in or nothing. So there are two levels. So the chemical treatment, with those levels, solution or nothing, that's what we're looking at. An experimental unit. So I'm going to argue these 10 tomato plants are in their own containers. So the 10 tomato plants. Keep in mind, if you have them in shared planter boxes, totally different. Way beyond the scope of this class, but it does become very different very quickly. So now draw a possible experimental flow diagram. So I'm going to just start. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. It's not the neatest ever, but I have these 10. In fact, it's going to look a lot like the last drawing. So I'm going to randomly select. So I'm going to let a computer do a random number generating. So 2, 3, 6, 9, and 4. So there's 5, and then the other 5 are going to end up in the other group. So now this group 1, they're going to get the chemical solution. This is group 2. They're going to get nothing. And then we're going to compare the results. So that would be one possible one. The things that would change up are just which 5 end up in the chem solution, and then the other 5 end up in the no chemicals group. So randomized experiments, there's another one that we're going to talk about. It's a completely randomized block design. So this is used when we have units that have some shared characteristics. So maybe you're aware of, hey, here are all my units, but I know that I have, this many, sexes, or I have this, many age groups. So you want to actually be sure that everyone, that every age group is represented. So suppose you have 5 age groups. You want to make sure that each of the treatment groups has all 5 age groups in it. That's the idea. So it's something you want to account for, although blocks are not usually what you're interested in actually studying. It's something that you need to account for because you know that these different groups exist, so you must record them, but they're usually not what you're interested in actually studying the effect of. And so it's really important you have to randomly assign within block to avoid confounding variables. So looking here, I have an example where I have circles and triangles, right? So there are these 2 different groups, and I need to make sure that I give each of these 2 groups both treatments. So the first step, I'm going to break them into blocks. So here's the circles, and here are the triangles. Then I'm going to randomly assign groups. So I have 2 groups of circles. One group gets treatment 1, one gets treatment 2. Then with the triangles, I do the same thing. I randomly select half the triangles to treatment 1, the other half to treatment 2, then I compare. And the idea behind this is if I do it this way, then I'm accounting for the impact of circles and triangles. It's a little weird to do it with shapes. I have an example, so I'm going to show you that example. That might help. So I have a bunch of bunnies, 100 rabbits total, and Healthy Bun is a hopefully made up name. They want to test their food formula on domestic rabbits to the old formula. They want to see if rabbits gain weight faster on the new formula than the old one. So they're concerned that lop rabbits, so lops have these, downward ears, gain weight differently than non-lop rabbits. Note that I don't know enough about rabbits to know if this would be true. The researchers have 40 lop rabbits and 60 non-lop rabbits. So basically we want to make sure that roughly half the 40 lop rabbits get the new food and half get the old food. And then half of the non-lop rabbits get the new food and half get the old food. So here, the lops are going to be triangles and the ones with the upright ears are going to be squares. So I'm going to break these into, I am not going to draw 40, but 40 lops. And I'm going to break it into 20 lops. 20 lops. So, and this is a random assignment. And so the new food, half will get the new food and half will get the old food. Same here with the rabbits that aren't lops. So I have 60 non-lops. That's a weird way to put it. So I'm going to use random assignment again. And I'm going to put 30, I'm going to put 30 rabbits into the new food group. And I'm going to put 30 into the old food. In this way, I'm accounting for the type of rabbit. Even though it's not what I'm interested in exploring, I really want to just know the impact of the food. I need to account for the type of rabbit. So then I'll compare. So compare results in that way. So that would be a setup there. So then there is a special case of the randomized block design. It's called matched pairs design. And chances are you might have heard of this particular design, whether or not you've used it. So matched pairs design is a randomized block experiment where each block has a matching pair. So there's 2 units in each block. And each pair is randomly assigned to their treatment. So where you see this a lot are an individual that has a pre and post or before and after score, right? So a person is one block, right? Their pre-score and their post-score, they go together. You don't want to separate them. You can do this also with 2 dependent or identical units that one receives one treatment and one receives the other. We're usually not fortunate enough to have identical twins, but I know that definitely scientists love being able to study with identical twins. So the idea is you have pair 1, one gets one treatment, one gets the other. You have pair 2, one gets one treatment, one gets the other. And which one gets which treatment is randomly assigned. For example, we have researchers, they're studying the effect of 2 breathing techniques. So our treatment is going to be the breathing technique. We have, technique 1 and technique 2. They went ahead and they want to look at the performance times for 10 college swimmers. And they have each swimmer swim the same stroke for 200 meters using 1 breathing technique. Give them a reasonable rest, and then have them use the other technique, and they time them both times. So the order of the breathing technique is randomly assigned, and their times for each run is recorded. So swimmer 1, they do technique 1 and then technique 2. Swimmer 2, they're randomly assigned to do technique 2 first and then technique 1. All the way through, swimmer 10 did technique 2 and then technique 1. That's the idea behind the paired. And so pre and post, or 2 different things on one individual's common. I know I participated back when I was doing my degree at Montana. There was a really smart of them, a bioscience lab across the street, and they would pay students or whoever to participate in studies. And one study, they wanted to look at the effect of ink on skin. So they took one measurement, whatnot, they put ink on my arm, on my left arm, and then they put a different ink on my right arm, and they recorded whatever it was they were looking for. So that's another example of a matched pair, where the idea is they can reasonably assume my skin would react similarly to, the skin on my other arm. So you keep them matched or paired. Okay, so this one's a little fun here. We have, if you like grass. So we have a farmer, they're really interested in buying a new fertilizer. They have turbo grow, and they have a field of Kentucky bluegrass. So that's a type of grass. And they have another field of ryegrass, and they apply Nutri-Green fertilizer to it. After a few weeks, they notice the ryegrass is growing much faster than the bluegrass. So what does this tell us about the fertilizers? So here, just looking here, looks like the Kentucky bluegrass, they went ahead and they gave the Kentucky bluegrass only the turbo grow. Then they gave the ryegrass only Nutri-Green. So here, turbo grow is less effective of a fertilizer than Nutri-Green. Maybe, but what if it's just the type of grass? We're not sure, right? So that's the problem with the first 2. So I would argue our answer is C. Based on how this is designed, we can't tell anything. The fertilizer type and the grass type are confounded. There's no way to tell if it was the fertilizer that caused the growth or if it was the type of grass, or maybe both. But because of the way we designed it, we can't actually tell what caused the extra growth for the ryegrass. So to continue on this one, so to reduce the chance of confounding, what type of randomized experiment should we use? So there are 2 designs here. So the idea is we're really interested in the effect of the fertilizer. However, we want to be careful and make sure that we control for the type of grass. So the first one is a completely randomized design. So that means that I had 8 plots, and I randomly assigned 4 of those 8 plots to have turbo grow, and the other 4 had Nutri-Green. But if you look here, it looks like 3 of the 4 plots for the Kentucky bluegrass have turbo grow, and only 1 of them has Nutri-Green, and that could be a problem. Versus design B, it looks like they went ahead and said, okay, I'm going to take the Kentucky bluegrass and give half of the Kentucky bluegrass turbo grow. So they randomly assigned half of those 4 plots turbo grow, and the other 2 got Nutri-Green. Then they did the same thing with the ryegrass. They said, okay, well, I have 4 plots for the ryegrass. I'm going to randomly assign half of them turbo grow and the other half Nutri-Grow, or Nutri-Green. So look in here. Okay. So in both cases, half of the Kentucky bluegrass has turbo grow and half of the ryegrass has turbo grow. This is going to be the one we want because this way we can guarantee that half of each type of grass has each fertilizer. Without it, it's really, really difficult to. Here, I would still be at odds to really definitely say that it was the fertilizer making the difference when you have 3 out of 4 plots being one type of fertilizer. So then, just a couple of cautions here. We're going to talk about placebo effect and then blinding. So whenever especially humans are involved, you want to be careful of the placebo effect. So first off, what is it? Chances are you've heard of it. So the placebo effect is that beneficial effect of a perceived treatment, whether or not there's any active treatment. So somebody believing that they're receiving a treatment, so that improving whatever's going on. Like, my little niece wasn't feeling so good, so I gave her an M&M and told her it would make her feel better. And then she's zooming around and she's like, oh, I feel so much better. Can I have another one? That kind of thing. Adults, it's usually less pronounced, but it still happens. So then how can we control for the placebo effect? So this is give the control group a placebo. That is, give them a treatment that, for all intents and purposes, it looks, tastes, feels, whatever, exactly like the treatment, except it's not the treatment. Like, it doesn't have the active ingredient. So if you have a treatment that's giving somebody a pill, you have to have like a sugar pill that looks just like that pill that you give the control group. That's the idea. So it needs to appear in every way like the treatment, except for the active ingredient part. So some cautions here. There was a weight loss supplement, and doctors wanted to study this particular supplement. So they informed patients about the goals, and they randomly assigned to take the daily supplement every day or nothing at all. And participants' weight is recorded again 12 weeks later. So possible issues. Any unintentional bias. So what we're getting at is, does the patient know, does knowing which treatment group they're in, does that impact the results? So there's this idea of blinding. So single blinding, specifically, it's when the individuals getting the treatments have no idea which group they're in. So they're unaware. So they might be given a placebo. They might be, a sugar pill that looks just like the treatment but doesn't actually have any active ingredients. Double blind, which makes us happier. So this is where the individuals don't know what treatment they're getting, but also the researchers don't know what treatment they're getting. And this is really important because some researcher knows who's getting what, but the researcher collecting or recording on the patients or the subjects, they don't. Because if you walk up knowing, oh, this person's in the program, that might impact what you look for and how hard you look for it. It might impact how you measure it. So the ideal is that the patient or subject does not know what treatment group they're in, and the researcher recording does not know what group they're in. So really, really important. Both really help to lower bias. So that's going to be it for lesson 12. That's it for week 3 content. And I look forward to seeing your comments.